So we will continue. So as I said, like if you look at the y1 value here, from the Euler formula, the first rough estimate gives you 1.2. And from the modified Euler formula, the first iteration gives you 1.216. And the second iteration gives you 1.2176. So up to two decimal places, the first iteration and the second iteration values, they agree each other. So but still, we need to find the value of y at 0.2 correct up to three decimal places. So since they do not agree for the third decimal place, we will have to continue with the third iteration. So the third iteration, the formula will be something like this from the Euler modified Euler formula. Fx naught y naught plus fx1 y1 from the second iteration. So by looking at this functional form, fxy is y minus x squared. So we will simply write from here, right? Y1 from the second iteration minus x1 square. So it will be 1 plus 0.1. X naught is 1, y naught is 0 square. So plus y1 from the second iteration is 1.2176. 1.2176 minus our x1, 1.2176, x1 is 0.2. So this is simply 0.2 square. So let me compute this again using my mobile phone calculator. So this will be 1.2176, 1.2176 minus 0.04. This is 1.1776 plus 1 multiplied with 0.1 plus 1. So what I have here is 1.21776. Now, if I compare the third iteration value of y1 and the second iteration value of y1, I find here that up to third decimal places, it is 217, 1.217, and here up to third decimal places, 217. So since our desired accuracy is only up to third decimal places, so we can conclude that our result is 1.217. Okay. So up to third decimal place, the second and the third iteration, they agree. So this is how we have to compute. And similar to that, you have to compute here. This same problem, you can continue and find the value of y at 0.4, correct up to three decimal places. So you have to find out, if you have to find the value of y at 0.4, what you're going to need is your x1 here is 0.2. All right. And you have to find your x2. X2 is x1 plus h. X1 is 0.2. Your h is 0.2. That means 0.4. So x2 is 0.4. And you can find your y2 from the Euler formula. From the Euler formula, y2 will be y1 plus h f of x1 y1. So using this Euler formula, you find a value of y2. And here your x2 is 0.4. You find a value of y2 also. Once you have the value of y2, you have to use the modified Euler formula to find the correct value of the three decimal places. So in order to do that, what you're going to calculate is y2 first iteration, y2 second iteration, y2 third iteration. Maybe you need to calculate the fourth iteration also. You have to see that for the consecutive iteration, the decimal points, they agree up to three decimal places. Yeah, they agree up to three decimal places. So this is how you have to solve the differential equation using Euler formula. Euler formula, from this Euler formula, once you know the differential equation and the initial condition, you can obtain the value of y. And more accurate result you can obtain using this modified Euler formula. So this is the one problem you have to do it. All right. You have to do this calculation. So here you will find that your x naught is 1 and your y naught is 2. So you have to find at 1.2. 1.2, if you have to arrive at 1.2, what you're going to need is your step size. You have to choose it to be 0.2, so that your x1 will be x naught plus h. X naught is 1 and h is 0.2. Then you will arrive at 1.2. So once you have x1 as 1.2, you can find your y1. Y1 you can obtain it using, what is that? Euler formula y naught h f of x naught y naught, right? Then using modified Euler formula, you can find more accurate result, correct up to 3 decimal places. You can simply use y1 first iteration. This will be y1. This will be, yeah, what is that? Euler formula y naught, right? Y naught plus h upon 2 f of x naught y naught plus f of x1 y1, like that. So the same steps you follow, but here you have to choose your h value as 0.2 in order to arrive at 1.2 from 1. So here your functional form f of xy is ln of x plus y. So you have to finish up this calculation. Now this Runge-Kutta formula, we don't need to go into the detail of this formula derivation. So something like this. Here, this is the differential equation with this initial value problem. Using this Taylor series expansion, we can find the functional form of y in terms of x, y at x. Y at x you can obtain using this Taylor series expansion. And if you remember, in Taylor series expansion formula, what we did was this dy upon dx is your y prime, right? Your y prime f of xy, right? So if you like at this initial value x naught y naught, if you put the initial value x naught y naught here, you will get y naught prime. And you can similarly, after differentiating this, you will get the value of y naught double prime, y naught triple prime. So this we have already done in the class. So using this Taylor series approach, one can obtain the functional form of y in terms of x. Once you have the functional form of y in terms of x, then you can find the value of y for any value of x, the value of y for any value of x, right? Now, if you compare with the Euler formula was y naught plus h f of x naught y naught. So you see that this differentiation y naught prime, it will be f of x naught y naught. Y naught prime is simply f of x naught y naught. Okay, so dy upon dx, like I said, dy upon dx, if you choose your step size del x to be very small or your h value to be very small, then your dy upon dx will be equivalent to differentiation of y at x naught. So the y naught prime is actually f of x naught y naught. This is what we have discussed in our Euler method. So if you look at this Euler formula here, your first point you obtain it using y naught plus h y naught prime. So x minus x naught, if h is your step size, x minus x naught is your h, right? So this first two term, the first two term of this Taylor series expansion is your Euler formula. So you can see that Euler formula is more approximation. I mean, even though this Euler formula is not very accurate at all, but it is the simplified form of your Taylor series expansion when you are taking up to the second term of this Taylor series expansion. You are simply using the second term of this Euler series, the second term of this Taylor series to compute the value of y. Okay, so instead of considering all other terms, we simply use up to the second term. So this Euler method itself is also considered as first order Runge-Kutta method. So when we consider the modified Euler formula, here, if you take this modified Euler formula here, again, this modified Euler formula is like in agreement or in coincides with Taylor series expansion up to the first three terms. So this Taylor series expansion up to the first three terms here, if you manipulate around it, you will arrive at this modified Euler method. The modified Euler approach, whatever we did, was similar to considering up to the third term of this Taylor series method. So this modified Euler method is also taken as second order Runge-Kutta method. Okay, so in the second order Runge-Kutta method, in order to find the y1 value, the value of y at x1, we use this formula. So here your k is h of f x naught y naught. Your k1 is this, k2 is this. Okay, and similar to that, this thing is called the third order Runge-Kutta method. And here up to first four terms of Taylor series expansion, it tallies with first four terms of Taylor series expansion. So how it tallies and all, you have to manipulate around with that Taylor series expansion formula a little bit. So let's not worry about that. And this Runge-Kutta method of order 4, this is what we are going to use the formula. This Runge-Kutta method of order 4 more or less is equivalent to the first 5 terms of Taylor series expansion. It is equivalent to the first 5 terms of Taylor series expansion. How it is equivalent, you have to derive a little bit formula here and there in the Taylor series expansion. Okay, so this Runge-Kutta method is equivalent to the first 5 terms of this Taylor series expansion. So this is the Runge-Kutta method of order 4. This is what we are going to use. Okay, Runge-Kutta method of order 4. Simply, you have to memorize this formula. You have no choice. Okay, so Runge-Kutta method gives you the value of y, that is y1 at x1. Using this formula. What is this formula? Our k1 is h of f of x naught y naught. Our k2 is this. Our k3 is this. Our k4 is this. So you have to remember all this formula. No need of derivation. Simply use this to compute or to find the value of y1 at x1. So this is like one problem you can think of. And you can use the Runge-Kutta method to find the differential, the solution for this differential equation at x equal to 0.1. At x equal to 0.1, and you can compare the numerical solution obtained using the exact solution. Exact solution you can calculate using integrating function and all. Here, dy upon dx is equal to y minus x, means your f of xy is again y minus x. And your x naught is 0, your y naught is 1, and here you have to compute at x equal to 0.1. So if you have to arrive at x equal to 0.1, you can choose your step size to be 0.1, so that your x1 will be x naught plus h. It will be 0 plus 0.1, 0.1. Like that, you can arrive at this point. X1 is 0.1 now. And in order to find the value of y1, the value of y at x equal to 0.1 is called your y1. Y1 is, you can simply use this Runge-Kutta method of order 4. Y naught plus 1 upon 6 k1 plus 2k2, 2k3 plus k4. 2k2 plus 2k3 plus k4. So this is the formula you're going to use. Your k1 is h into f of x naught y naught. K1 is h into f of x naught y naught. So your step size here is 0.1. F of x naught y naught, y naught minus x naught. This is the f of xy. So here you will see that 0.1 into y naught is 1 minus x naught is 0. So this will give you 0.1. This is your k1. Now your k2 is hf x naught plus h upon 2 y naught plus k1 upon 2. So your k2 will be h function of x naught plus h upon 2 y naught plus k1 upon 2. Y naught plus k1 upon 2 x naught plus h upon 2. So h is 0.1 you have chosen, 0.1. F of x naught is 0 plus 0.1 upon 2 plus y naught is 1 plus k1 is 0.1, 0.1 upon 2. So this will be 0.1. F of 0.1 upon 2 is 0.05, isn't it? So 0.1 divided by 2 is 0.05. So this is 0.05. This is 1 plus 0.05 will be 1.05. 0.05, 1 plus 1.05. Okay, so this will be 0.1. And if you look at this, f of xy is y minus x. So this will be y is this, x is this, 1.05 minus 0.05, and here 0.1 into 1. So this is again 0.1. Now your k3 is this formula. K3 will be h of f of x naught plus h upon 2 y naught plus k2 upon 2. So h is 0.1. F of like this, x naught is 0, 0.1. Same thing you will get. Y naught is 1, k2 is 0.1 upon 2. So if you compute this, you will get k2, k3 also as 0.1. If you compute this, k4 will be, what is k4? hf x naught plus h, y naught plus k3. hf x naught plus h, y naught plus k3. h is 0.1. F of x naught is 0, h is 0.1. Y naught is 1, right? Y naught is 1. K3 is 0.1. So this is 0.1. F of 0.1, 1.1. So here again 0.1 into, what is the functional form? Y minus x. Y is 1.1 minus x is 0.1. So this is again 0.1. So once you obtain all these values, you put in this formula. So in this formula, all these things are 0.1. That means your y1 will be equal to 1 plus 1 upon 6. K1 is 0.1, 2 into 0.1 plus 2 into 0.1 plus K4 is also 0.1. So if you compute here, this is what we are going to get. 0.2 into 0.1 is 0.2 plus 0.2 plus 0.1 and 0.1 is 0.2, 0.2 multiplied with 1 divided by 6. Yeah, this is what we get, 1.1. Okay, so this is the result, we obtain using this Runge-Kutta method. And you have to compute, you have to compare with the numerical solution of this. So in order to find the numerical solution for dy upon dx equal to y minus x, use this formula. Okay, this is the integrating approach, integrating formula. So our differential equation is dy upon dx is equal to y minus x, y at 0 is equal to 1. So here you can write like this: dy upon dx minus y equal to minus x. So here you see that the coefficient of y is px. Your px is minus 1. The coefficient of like whatever term on the right hand side is called your qx. Your qx is minus 1. Okay. So integrating factor is qx is minus of x. Sorry. Integrating factor is this. Your integrating factor if, your integrating factor is e to the power integral px is minus dx. So your integrating factor is e to the power minus x. So you just multiply this equation. Sorry, you just multiply this equation with your integrating factor. So what we have is dy upon dx minus y into my integrating factor is e to the power minus x, e to the power minus x. The right hand side is minus x into the power e to the power minus x, minus x e to the power minus x. Okay, so this will be like this: dy upon dx e to the power minus x plus y into differentiation of e to the power minus x dx. So if you look at this, if you multiply here, you can, if the first term is dy upon dx into e to the power minus x, so if you multiply with this, we will get minus of y into e to the power minus x. Minus of y into the power e to the power minus x will be same as differentiation of this. If you differentiate this, you will get minus of e to the power minus x, right? So this second term will be same as this. So if you rewrite this d upon dx, you can write this as y e to the power minus x e to the power minus x. So integrate both sides after multiplying with the integrating factor. If you integrate both sides, if you integrate both sides, the left hand side will be simply y e to the power minus x. The right hand side will be minus of x e to the power minus x dx. Okay, so you can use the integration by parts. What is the integration by parts formula? Y e to the power minus x. I think you can continue here. You can take what is that? One of these function as the first function and the second function. Let's say we take e to the power minus x as the second function. Just a minute. So how do we approach this? I think you should be more familiar with this calculation than me. What is that integration by parts formula? I just forgot. Just let me check. Yeah, okay. So I think if I remember correctly, where is that? So it was something like this. You remember there is a minus sign here. Integration by parts was something like this: f of x gx dx, it will be f of x into integration of gx dx minus integration differentiation of the first function into differentiation of the first function into integration of the second function again, I think, and the whole term you have to integrate, something like this. Okay, so y e to the power minus x here minus x you take it minus x you take it as the first function f of x, and e to the power minus x you take it as the second function g of x. So let's do it like that. So f of x is minus of x integration of e to the power minus x dx minus integral differentiation of f of x. Our f of x is x, that means this differentiation is 1, and integration of e to the power minus x dx. So this will give me e to the power minus x integration is, I think e to the power ax dx will be e to the power integration of e to the power ax dx will be e to the power ax upon a, right? So a here is simply minus 1. So this is minus of x e to the power minus of x upon minus 1. Minus 1 and minus 1 will cancel out. So here this is also e to the power a of x. Integration will be e to the power a of x upon a. So this will give me e to the power minus x upon minus 1 and dx. So minus and minus cancels out. Now if you integrate this again, so here you have the first term x e to the power minus x. Integration of minus x will be minus of e to the power minus x plus, let's say, certain integration constant. Okay, so here your y, oops, this is one of the problem I was supposed to give you. Y will be equal to x minus 1 x minus 1 plus c into e to the power plus of x. So here on the left hand side you have e to the power minus x. So if you transfer e to the power minus x of x to the right hand side, this is what you're going to get. And here you have this. What is that initial condition we have? Our initial condition is this. So let's use the initial condition here. Initial condition is this. So y naught, y at x naught is 0. X naught is 0. Your y naught is 1, right? So x naught is 0 minus 1. Y naught is 1. Y naught is 1 plus c e to the power x naught is 0. So this will be 1 minus 1. If you transfer the right hand side, this will be 1. C e to the power 0 is 1. So c will be 2. So if you have c as 2, then your functional form is y equal to x minus 1 plus 2 e to the power x. So this is the functional form we have. Now, what was that? Yeah, we have to find at x equal to 0.1. X equal to 0.1. So at x equal to 0.1, once we obtain the solution like this, y1 will be 0.1 minus 1 plus 2 into e to the power 0.1. To calculate exponential of 0.1. Exponential of 0.1. Exponential of 0.1 exponential of 0.1 is almost finished. Sorry. 0.1 minus 1 plus 2 into exponential of 0.1 is 1.105171. 1.105171. Let me just compute. 2 times 1.105171 plus 0.1 minus 1. So here what we have is 1.31. Okay. So this is the result we obtained using the exact solution approach. And using Runge-Kutta method, what did we obtain? 1.1. So I think there's some error here. All right. So anyway, that is the approach. So in this Runge-Kutta method of order 4, you have to use this formula. You can compute K1, K2, K3, K4, and you can obtain the approximate solution at Y1. You can compare with the exact solution like that. So this is again another problem. You have to do it. Okay, please calculate this particular problem. So I will upload this video in your WhatsApp group if possible, and you can calculate all these things. So I think I can end the session.